Hello and welcome to my presentation about the paper I read, which has probably the longest title ever. It is Science Objectives for Flagship Class Mission Concepts for the Search for Evidence of Life on Enceladus. So what does this mean? Like summarized, the people who wrote this presentation wanted to give a good basis to a mission who would go to Enceladus and search for life there. And actually, the search for life, evidence of life, has been as old as the space age itself. But since the Viking probe from the 70s, no specific mission has been designed for the search for evidence of life elsewhere in the solar system. And on life, we found that beneath kilometers of ice in deep sea thermal vent, it might have been the start of the life on Earth. And that's why ocean worlds or ice moons have become very interesting for astrobiologists to study. And there has already been a probe which orbited Enceladus, and this was Cassini. That's, for example, a picture that Cassini took. And here you can see the moon Enceladus with its very icy surface. And thanks to this ice, it has the biggest albedo of any celestial object in our solar system. It also is geologically active and gets heated so that at the South Pole, you can see here, there are plumes of water ice emitting. So why the moon is geologically active, we still don't know exactly, but it's partially because of the interactions with Saturn. It is also tidally locked, so it's always facing the same side, Saturn. And Cassini has already shown that there is a subsurface ocean beneath the thick layer of ice. But the information we gathered from Cassini isn't sufficient enough to say if there's life on it or not. That's why scientists want to revisit this moon. And in the paper, it is demonstrated how we should go about doing that. So here you can see the plumes of water ice, also a picture of Cassini. And these get ejected into space and form a so-called E-ring around Saturn. Enceladus ring, for short. This is outside of the rings we usually think of when we think of Saturn. And yeah, it's the ice particles which form a big layer around the planet. Okay, now NASA has a committee which is meant to guide the exploration of ocean worlds in the several next decades, and it has forth-put like a strategy to search for life on ocean worlds. Like the first point would be identifying ocean world, then characterizing their oceans, evaluating their habitability, searching for life, and if we found life, characterize it. So the special thing about Enceladus is that from the data of Cassini, we can already check off the first three points of the list. And it is so far the only world which meets these three criteria. The paper also demonstrates how to search for life, and there are basically two questions we want to answer with a mission. I'm gonna come to that shortly, but first, what kind of mission is planned? So an ideal mission would be for a single spacecraft called Orbilander to orbit around Enceladus a few times and then eventually land on the surface and collect some more samples there and take measurements. So, what questions does the Orbilander want to answer? The first one would be, is Enceladus inhabited? And the second one is, to what extent is Enceladus ocean able to sustain life, and why? I'm gonna go a bit into detail with the first question now. So, is Enceladus inhabited? There are some methods to search for life, and one of them is the molecular assembly index. So we can ask ourselves how much of the samples or how much of the materials we collect are organic or inorganic. So molecular self-assembly is the minimal amounts of steps a molecule would have to take to get into the shape. So complex molecules have a lot of steps they have to take until they're finished, and simple ones only a few. So complex molecules have a high MA value and simpler molecules don't. And so far, we only know of life to produce molecules with high MA values. So that would be a first indicator for life. This can be measured with a mass spectrometer, which determines the weight of certain molecules, the molecular weight. Okay, next off, we have the amino acid characterization. So amino acids can be produced either through abiotic or biotic processes, but you have certain attributes which can determine if there is life or not. One of them is the abundance pattern. So life on Earth prefers certain amino acids to do certain proteins, like some amino acids are used more than others, and these relative concentrations of amino acids could be used to determine if there is life or not. The other one would be chiral excess. Like some of you may already know what chirality is, but for those who don't, I'm gonna explain it shortly. So here you can see two molecules, D-glucose and L-glucose, and these are mirror images of themselves. And at first you may think, oh yes, they're the same molecule, but if you try to turn them and put them into the same position, you won't succeed. But they both have the exact same chemical properties. So same condensation point and so forth. But we see on Earth that life only uses L amino acids. So it only uses one of two enantiomers. Why it only uses this is not known yet, but there are also some exceptions. But we think that if there is life, it preferentially uses only one of these two. So if you find a racemic mixture, which would be like 50% D and 50% L enantiomer, you would know that it is from an abiotic process. But if you find an excess, so for example only the L amino acids, you would know that there is life, or these amino acids stem from life. This can be measured with a polarimeter, which sends light through these molecules and observes in what angle the light comes out. So they can determine if it is a D or an L amino acid. Next up, we can also characterize the lipids. So life uses lipids for their membranes. And these membranes can be characterized through their lipid composition. So life on Earth only uses lipid chain lengths of between 12 and 30 hydrocarbons, but preferentially from 16 to 18 hydrocarbons. Because if you go lower than 12, you get volatile, so very fluid layers. And if you go higher than 30 hydrocarbons, you get waxy layer, which is difficult to use for anything. These cell walls are also characterized by the amount of double bonds in them. So here you can see that if you have more double bonds, your layer gets more fluid. And the same thing is with addition of subunits. So here you can see that if you add some subunits, these distances get larger and the layer also gets more fluid. The good thing about lipids is that they can persist over a long period of time. So the probability is very low that they get changed when ejected to space. This can also be measured with a mass spectrometer. We can also search for polyelectrolyte chains. These are chains of very long charged molecules. And one example of that would be pectin, which is embedded in the cell walls of plants. And it gives stability while keeping their fluidity intact. So these long chains of charged molecules are thought to be unique for life capable of Darwinian evolution. That's why it is a very strong indicator for life. The thing is, they are pretty unstable, and there's also big chance of terrestrial contamination. This means that we could bring these molecules or even whole organisms to Enceladus and detect them there, and then lead to the conclusion that we found alien life, but actually it would be the life we brought with us. So that's why the Orbilander would have to be built in very sterile environment. And it is also the reason why Cassini ended its mission in 2017 with burning up in Saturn's atmosphere, so that the moons of Enceladus don't get contaminated with life from Earth. We can also search for cells directly. This would be a very strong indicator for life, but we can't only search for the morphology of a cell, but also its movement or autofluorescence, which is also very common for life on Earth. For example, you can distinguish the random motion, called Brownian motion of molecules, from the directed motion of cells. Brownian motion is, for example, if you put your tea in the hot water, it will randomly and evenly distribute, and this isn't seen for life. This would mean, though, that the cells would have to remain alive even when getting ejected out to space. And this is not very probable, or we just don't know. This you can observe directly with a microscope. which the Orbilander will have several of them. So next we want to answer the question how habitable the ocean of Enceladus is. So we want to characterize the physical and chemical environment of the ocean. This is very important because these interactions the ocean has with the rocky core can produce certain elements or products which are important for life to exist. Some of these products Cassini already analyzed, but we don't know enough to really assess the habitability. We also want to know if there are hydrothermal conditions in these oceans. Like on Earth, it's very possible that life formed like this in hydrothermal conditions. But you have to check a few things first. So you have to have the right amount of pH, multiple temperatures, phosphorus, and redox reactions. And this chart shows how we could search for an hydrothermal condition on Enceladus. To the right, you can see these two. These are the payload elements. So HRMS stands for High Resolution Mass Spectrometer, and ESA stands for Electrophoresis Sensor Array. These would detect these things and try to answer these questions. So here you can see that you have to have a pH lower than 12. And this can be measured by measuring different ionic distributions from some elements, like carbon, hydrogen, nitrogen, or phosphorus, for example. And also through the isotope distribution of many elements. And also if there are these redox reactions, you can observe that by measuring the amounts of phosphorus and sulfur, as they act as molecular carriers for these redox reactions on life on Earth. Then we also want to know more about the structure and the dynamics of the interior. This can be done with seismic measurements and also through thermal observation of these jet vents. Then you also want to know how the plumes get ejected to space, because you want to know how representative the material in space is of the ocean, which is underneath the ice. And also you want to know if there is life, how much of it would actually get ejected to space and survive. Here is a chart that represents that how much cells there would be per milliliter of collected water. So you can see here, just in the ocean, there would be very little cells available. Then here in the plume, there would be more, but this is pretty uncertain, as you can see here, by the orders of 4 magnitudes. And the cells expected to be at the vents, this number is very high. So you can see the hydrothermal conditions are really important for life to exist. And this was measured with Cassini's data. So basically it was compared to similar environments on Earth and the energy available. Here you can see, for example, on Earth, the Pacific sea floor sediments are pretty similar to the expected Enceladus plume. But you also want to know how big the particles are that you collect. So in 40 kilometers altitude, the particles are much smaller than on the surface, or like lower in the atmosphere. But through all these measurements, we know that the Orbilander only would have to collect 5 milliliters of the sample to get a significant result. So all these measurements are taken with instruments which are grouped into 3 groups. First, we have the life detection suite. This would go on searching for life on Enceladus, and it would do so with the help of a mass spectrometer, which can differentiate between organic and inorganic material, as well as characterize the amino acids and lipids. Then you have an electrochemical sensor array, which would assess the physiochemical environment of the ocean and the mechanisms how this material would get ejected. Then you have an electrophoresis device, and this can also characterize amino acids and lipids, and is used to separate molecules based on their size and electrical charge. Then you have a chromatograph assessing the chirality, and a nanopore sequencer, which would detect polyelectrolyte chains with a flow cell. And then you would also have different microscopes to search for cells or the motion of those cells. Next off, we have the remote sensing and reconnaissance suite. This would be basically used to find a landing site for the Orbilander, which would be assessed with a wide angle and a narrow angle camera. Then this would also have a thermal emission spectrometer, which can determine the structure of the vents, because at the vent openings the water would be hotter than outside. So this can really help with characterizing the structure of the crust and how it gets emitted. Then you also have a laser altimeter, which stands for altitude meter, and this would be used for the landing, but also to map the surface topology and the crust. So here you can see it being used on Mars. So the blue areas are areas which are very low, and the red or even white ones are the parts where it's further up. So it basically measures the altitude. So the laser gets shot at the place, and the time is measured how long it would get to get back. Then you also have a radar sounder, which would also assess the structure of the crust and the jet vent openings. And next off, we have the in situ suite. In situ means on site. So this would basically be when the Orbilander has already landed. So for the final stages of the landing, you would need a context imager. And then later, if it has landed, you can use a seismograph. There are also seismic events on Enceladus, expected to be twice a month or more. And the seismograph can also, complementary to the radar, assess the structure of the crust and the jet vents. So now to the conclusions. This study has shown that a return to Enceladus would not only be well motivated by Cassini's data, but also really achievable with today's or in development technologies. And it has also shown that there can be a robust and compelling case made for evidence of life if we search for it, like presented in this study. This could be done in less than a decade. So I found this paper very interesting because until now I didn't really know how we would even search for life on other objects. But now I can be certain that if we would do these measurements, that we would have very clear detection, like a positive or negative result would be really significant. I actually hope that there is life on Enceladus, but it would be really interesting for me if you could post or comment if you think there is life or if there could be life on Enceladus. But I think it would be really exciting, and it also excites me that this mission would be possible in less than 10 years, so we could all see if there actually is life on Enceladus or not. And with that, I really want to thank you for your attention, and please ask anything. If anything was unclear, just write it in the comments. Thank you very much.